Maybe, so just before I start the sharing, I also have a normal looks just out of the clean room because we are actually putting together the detector right now. And I thought it would be kind of cool to share this with you to some degree. I'll have photos anyways, and when I come to the photos, I can literally walk around and also show you what we're building with the detector, what we're currently doing later on with P1. That's why I thought it would be nice to do it from here. So let me share my slides. There is one more. Let me just. I'm not didn't want to do this. So I'll just try to move the view in the side so I can actually see if there is something up or something. Okay, excellent. Do I admit the people or do someone else admit people?
I can get that, yeah.
Okay, excellent. All right, so I'll tell you a little bit about the Pacific Ocean neutrino experiment and what we can do with that. First of all, I thought it would be kind of fun to tell you a little bit who I am because probably you don't know this. So I graduated from Munich. I'm actually currently there in a sabbatical. Just this week, I'm back in Vancouver. So that's why I'm speaking out of triumph right now. I then did my PhD at Stockholm University and I worked for IceCube, which you can see a few pictures down there. And I will mention a few things about IceCube. IceCube is a very large neutrino telescope South Pole. You see some fun hero shots of actually building the detector at the time at the South Pole, holding massive cables around. So that was a good time. And then I joined, came to Canada as a postdoctoral fellow and joined the Atlas experiment, and then changed from UBC to SFU in the same city to essentially become faculty. So I also mentioned this because lots of people always ask me what where the careers go and not, in terms of fields. True, I stayed in particle physics, but it's quite some drastic changes I did in particle physics as well. Right? So you can move around and see what you like best as well in many ways. I mean, you don't have to go all one-dimensional when you choose your path. Along the way, there were some fun things. So I also from Sweden, I took a boat and did some cosmic ray measurements all the way to Antarctica and almost around Antarctica and the way back. So it was a good time in the Swedish icebreaker. Probably that's why I got acquainted and want to do ocean things now. And as I said, what I do today, I still work on Atlas. So I work quite actively on Atlas, and I hunt for new physics, for signs of new physics. And I also work with this so-called P1 experiment, which I will tell you all about now. And also recently became the spokesperson for this experiment and will be the spokesperson from January. Okay, so I don't know how many particle physicists or students who only study particle physics. This is the picture we have. This is our standard model of particle physics, or one of the representation of all the elementary particles we know of. We have discovered the quarks at the top. There are different ways how to show this. This is one I like. At the bottom, we have the leptons, we have the gauge bosons, and in the center, in this case, we have the Higgs boson, which we found at the LHC. So I will talk. What comes next? No, okay. Then I don't have a mouse. So I will talk essentially today about the neutrinos, and not so much about the neutrinos itself in terms of the properties, what they are, actually how we can use them to do astroparticle physics and to some degree even astronomy, so neutrino astronomy. And of course, I really like it. You've seen it because I flashed it before. What I always really like to show is this is a beautiful, simple picture. You can convey the idea of, when you dive into it a bit, what holds the world together. But actually, when you put the math behind it, it's quite brutal. So that's always the benefit of some beautiful representation of some images, where actually there is a short big work behind it. And this is also a bit the kind of the topic of the talk. I try to give you a nice, accessible introduction to the field and to the experiment. If you have any questions, you can also interrupt me, ask later on. But of course, there's like this huge math behind it. There's quite a bit more behind it, which is of course not a good idea for such a brief talk. Okay, so if I talk about neutrinos, we should talk a little bit where neutrinos can come from, because that's quite important also to the story of what we want to do. And neutrinos are generally something that is tracing nuclear reactions. And so that's why we find a lot of sources, if you go around this here, in terms of what we have anything to do with nuclear reactions. So nuclear reactor produces a lot of neutrinos. The Earth actually has a lot of nuclear reactions. We can go back to the Big Bang. So they're these relic neutrinos. They're very, very low energy. I'll show you a spectrum in terms of energy in a moment. Supernova, of course, emits a lot of neutrinos. You heard probably of the sun. It picks up or emits around 100 trillion per second. And so also our body. So if you look at this, there's a number of sort of several 100 million per day that you actually emit in neutrinos. And of course, we have learned how to accelerate them and also make kind of beams. The interesting thing is what we do in terms of in the lab, if we want to produce neutrinos, is exactly the same what nature does, just nature can do it quite a bit better. So if we look at the image, it's actually kind of, I don't have, let me just see whether I'm not with my mouse back. Continue sharing in a second. Yeah, nice. No. I don't know about less minutes. Okay. All right, so I have to describe it. I'm sorry. So what you can see here is essentially how we produce neutrinos in the lab. So this little accelerator is supposed to be the triumph magnet, so the triumph accelerator, for example. You accelerate protons, and then you dump protons into a target. When you dump them into a target, you essentially create a lot of charged particles, so these pions and also these muons. And then from these muons, you can, when they decay, and the pions, when they decay, you get a lot of neutrinos. So everything else gets absorbed in this kind of media. You can put walls in between, you can have magnetic fields where you deflect the charged particles. And essentially what you get out at the other end, only the neutrinos can go through the wall, and you will see, you will have created a nice direction in the beam. So, as I said, nature does exactly the same. We just change like the accelerator we can build, with basically the best things we can build on Earth, with a bit more powerful accelerator. Something like, for example, a supermassive black hole has huge magnetic fields, can accelerate particles to incredible energies. And then you can dump this into a target, and the target would be a nearby radiation. It could be matter, it could be just also photon fields, essentially just something where you can dump your accelerated particles, in this case protons. And then you have exactly the same interactions. So accelerated charge, cosmic rays, plus a photon can produce these neutrons and the charged pions. And then you have the charged pions, and they decay, you get neutrinos again. And if you have the neutral pions, when they decay, you get photons. So this is how the universe essentially can create these extremely high energy neutrinos and also photons, or what we call usually gamma rays. So when we look at the spectrum of neutrinos from the universe, so on the y-axis you have a flux, on the x-axis you have energy in huge, like it's like almost, what is it, 25, 20, 26 orders of magnitude. And you have the neutrinos from the cosmic neutrinos, essentially at very, very low energy. Then we can, towards the neutrinos from the sun, we actually have managed to detect them, as you know, and then we get to the atmospheric neutrinos or the astrophysical very high energy neutrinos. So if we see kind of what we have detected or associated, so we're doing not too bad. So for a while now, probably quite famous in Canada because of the Nobel Prizes, from snow as well. So we have found the solar neutrinos. We have seen the atmospheric neutrinos. We have one supernova where we found neutrinos, the famous supernova 1987A. And we have also been able to identify neutrinos or very astrophysical neutrinos with an active galactic nucleus. So these are these very high energy sources. When I overlay a little bit the window, what we can do with these neutrino telescopes, then you can see we can do the very high energy end of it. So we cannot do solar neutrinos or anything below that. So we start basically being able to tap the atmospheric flux of neutrinos, and then we want to see as far out in energy as possible. So I give you here a super, super simple aptitude if you want to do or do astronomy with neutrinos, and I apologize if it's so simple, but I think it's always, I use it in public talks and I love it enough. So when you look at your hand and you injured your hand, let's say I bike a lot, bike on the weekend as well, you have an injury and you don't know what the injury is. Luckily, you can look in different wavelengths, so to speak. So you have X-rays, which can show you if your bones are broken, you have an MRI, if you have any soft tissue or ligament damage. Maybe what we don't do so often at the doctor, you have an infrared picture of your hand. And let's say you can see where your blood vessels are closest, to your skin. Not usually used in doctors, but you get the analogy. It's quite impressive what we can do to study our hand. And of course, astronomy has done exactly the same. So this is the Crab Nebula, so a very famous object. And depending on what you use so this is all the electromagnetic spectrum, of course, going from lowest energy, radio, infrared, the visible light, and it's a false image, but it's visible light at the top right. And then if you come to the ultraviolet, where you get higher and higher in energy, you start to see interesting new things appearing. In the ultraviolet, you can start to see a kind of a core of it. In X-ray is actually kind of the most amazing picture of this. You can kind of see the spiral infall into a central object when these jets emitted along the axis. And then if you go to the highest photons we have, to the gamma rays, you can really see the neutron star in the end kind of shining really bright in gamma rays. So we have learned really a huge deal, and this is the analogy of the hand, of course, if we look at different wavelengths and we can dissect these astrophysical or astronomical objects. So the question is, of course, how would this look in neutrinos? The interesting thing is also with neutrinos, as I said, it traces nuclear reactions, so you can really look inside and not only what happens on the outside. Okay, so what else is interesting? So if we look here, for example, we look what we can observe in the universe. So we go, again, huge amount of energy in terms of decades on the x-axis, where now in the y-axis in distance. So how far can you go to the galactic center, nearest galaxy, or you can go really far away to cosmological distances. And on the top, you can see kind of depicted a little bit the images, what energy range that corresponds to. Also the cosmic microwave background, if you heard of it. Infrared or optical, what usually our telescopes work, X-rays, gamma rays goes higher and higher in energy. The interesting thing is that there is a huge range, which you can see this black blob, which is essentially transparent to as opaque to photons and transparent to neutrinos. So this is where the universe, because you get a pair production, so two photons, so you get one of the very high energy photons, which can create a resonance and essentially pair produces with the CMB photons. So you cannot look into the universe with photons of these energies and these distances. So you have a huge deal, like in the furthest away and also the most powerful part of our universe, which we essentially cannot look into with our normal means. And the neutrino, of course, is a way to look really deep into these distances and also into these very energetic universes. Okay, so what else is important about neutrinos? So if you have, let's say, here's a little image of a, let's say, a rotating active galactic nuclei. So infall black hole in the middle, and then like protons get, for example, accelerated along this jet axis, lots of power, and you can emit protons, photons, and neutrinos. So what's the difference? What we have? So first of all, we can observe protons, and we do this quite well. But of course, these are charged particles, and the distance between when they're emitted and to us, we have very strong intergalactic magnetic fields, so they get deflected, and you can observe them, but you don't actually know where they were emitted from. So it's not a good call for astronomy. If you have a medium in between, we know photons work overall pretty well, but of course, photons get absorbed, get maybe redshifted or blue shifted, so it's also not ideal in terms of observation. Of course, what is excellent if you have a messenger like the neutrino, which just goes through absolutely everything unhindered and is not deflected, absorbed, or anything. That's why we call also the neutrino the perfect messenger, because it is electrically neutral. It's essentially massless, it has a very small mass. It's essentially unabsorbed, and it tracks these, as I mentioned before, these nuclear processes. So it's very interesting. You can understand more the inner works of the star and what is going on, instead of just seeing the outside interaction of, let's say, photon fields. But of course, all these fantastic messenger properties make it exceptionally difficult to detect, because if it goes unhindered through everything, it also generally goes unhindered through everything. So if you want to detect neutrinos, what you do is you try to find water or ice. I talk here about really large, with high energy, so really large detectors. Of course, this also is kind of true for, if you heard of supercamukanda or hypercamukanda experiment. These are also very, very large, but we talk here even larger. So water or ice is a perfect medium to detect that because of something that's called Cherenkov radiation. So if you manage to implement essentially a large body of water or ice with little cameras, which are photosensitive, then the neutrino, which comes from the bottom right, sorry, I have my mouse, so interact somewhere in the ice or close by. It can be actually quite far away at these energies, and it can create an electron or a muon, for example. In this case, the muon is a charged particle. It travels faster than the speed of light through that medium. So that's important. Of course, you can never be faster than the speed of light in vacuum, but through that medium, it travels faster than the speed of light. And due to that, you emit a very characteristic radiation. It's called this Cherenkov radiation. I think I have so the Cherenkov radiation, you can imagine it a little bit like a sonic boom, for example, from aircraft. Yeah? That's why, because you're kind of supersonic, or superluminal in this case, and you emit on a very characteristic angle these photons as this muon traverses your detector. And for detectors, they essentially detect the timing of these photons and the amount of these photons. And when you do that, you can reconstruct back the part or the charge track of this muon or this electron, and from there on you can infer back in the direction of the neutrino. So you actually never see the neutrino itself, you only see the products of the interaction of the neutrino in your medium. Okay, so the next part is exceptionally interesting to talk about all the great things IceCube has seen, but I want to talk to you predominantly the rest we talk about P1. So I do this very quick in very cartoon way, but please ask me more if you want about so-called IceCube's legacy. So IceCube was my PhD experiment. It was really exciting, and it's of course also a fantastic way to get ever to the South Pole. So you can see here the South Pole Station. It's a humongous detector. So the South Pole is roughly 3 kilometers of ultra-transparent ice. And the detector is buried between 2.5 and 1.5 kilometers in the ice. And it's kind of a hexagonal shape. And you can see the footprint there in the ice roughly. So of course you can't, it's quite tricky to get there. So you travel there by the plane, you can see. And the image on the top right is actually one of the last optical modules we deployed in 2011. So what we have learned is a little cartoon image of a history of this whole kind of field. It took quite a while. As you can see, there was an idea in 1988 already. Then Amanda, a predecessor, very small compared to IceCube, was completed in 2000. That was good enough to measure atmospheric neutrinos or detect atmospheric neutrinos. As I said, in 2011, it's actually the last season when I was there as well, we completed IceCube. And it's taking data ever since. It's actually a fantastic experiment with hardly any failure rate. And in 2013, they have discovered astrophysical neutrinos. So these are very high energy. In 2018, they have discovered or identified these with the first source. So we call it here is TXS source, or they call it Texas source. It's an active galactic nucleus, so with very, very high energies. It's maybe more for experts. They identified a neutrino at the glacial resonance. It's a very particular interaction in the ice. And then it continued on from there. So in 2022, a second source was identified. And in 2023, one of the biggest puzzles I'll show you as well, like in the first source you kind of expect to see is our own Milky Way. Like by pure spatial arguments, you think to see the things that are closest to you the first time. And it was very hard for IceCube to see that. And that is predominantly from the location. But this is, I just want to show you this also a little bit. So again, you can, maybe you've seen from NASA, these very nice and famous image. So this is a slither of our Milky Way in the optical, so right along the optical. Then you can, from the optical, you can go to very high energy photons, so these gamma rays. And so you can see also the galactic plane here in the red in the middle, emits very bright gamma rays. And it's shining really bright. And you have individual dots everywhere, which are very bright sources of gamma rays. So as I said in the very beginning, you can relate gamma rays, so high energy gamma rays, and neutrinos. So when you believe this picture that you accelerate protons and you dump protons into a target, say photons, then you create kind of a fixed ratio of neutrinos and high energy gamma rays. So you can make this prediction, and you can see that's the third one of there, where you can predict from the observation of these gamma rays where you would imagine to see neutrinos. And then you can see the fourth one is kind of the analysis expectation, because it's very hard to see the neutrinos for IceCube. The reason for that is the galactic center is for IceCube at the South Pole above the hook, like if you just look straight up. Neutrino telescopes are traditionally built that they use the Earth as a filter, and they try to observe neutrinos from which go through the Earth. So this allows you to differentiate between downgoing cosmic ray showers, which are kind of your background, to upgoing events, which can only be neutrinos, because no muon could traverse the whole Earth. But that makes it also very hard for a source that is above you to identify. So IceCube did observe, let's say, an excess of these neutrinos, but it's of course very blurry and not very good at this. But they did. So why we want to drive this field forward is literally IceCube has tapped this new field. But it took like more than 10 to 12 years of data. So it's an experiment which is just at the threshold of being good enough and sensitive enough to discover these things. So now you have a field which is guaranteed new science, and you want to tap into this. So basically by improving this by an order of magnitude, roughly the sensitivity. So we want to resolve the sources of our own galaxy. We want to know what more sources. We want to see what are the sources that create these very high energy astrophysical neutrinos. What I haven't discussed here, you can also with these experiments study the neutrino itself. And so it's actually very exciting what we can do, and use it for new physics searches, right? Because of course, when they're created, maybe there you have new physics, or the new physics could essentially automate the path of the neutrino it takes towards you. Okay, so then the question is, of course, can you now go also fishing for them in the ocean? And as you've guessed, the idea is obviously yes. So what we're trying to do, we try to expand this neutrino network. And here you can see currently neutrino telescopes all over the world. IceCube is at the South Pole at the bottom. There's one in the Mediterranean. There's one in a lake in Russia. And then what we are doing, as you can see here, Q1 at Ocean Networks Canada, is the new initiative for the time to push for a new neutrino telescope. I'll skip that. If some of you have seen this, there was a very, very high energy neutrino event observed by the Mediterranean telescope. If you have questions, I can come back to that later. Okay, so let me tell you a little bit about Ocean Networks Canada, because you might, of course, ask yourself why and if you want to do this now in Canada and not somewhere else. And the reason is you need, of course, a very dedicated, large infrastructure. And Canada has essentially the largest and the most capable ocean cabled network. So here's a general overview of kind of what ANC does. They operate also in the Atlantic Ocean and the Arctic Ocean, but what we are most interested in, what you can see on the left side, is the largest observatory they have, the so-called Neptune Observatory, which is just outside of Vancouver Island. So this is essentially an 800-kilometer loop of optical fiber cables, and you have quite a large power, which is distributed to several nodes, and you have a pretty decent data transfer. So you can imagine you bring your experiment, and you can kind of plug it into a cable, get power, and you can transmit your data. So that is roughly the idea. And what we are looking for is a site which is called the Cascadia Basin, which is circled there. And you can see on the artist image what we are aiming to build on the bottom line. All right, so the thing is now you just don't want to just go bigger. As always, you maybe want to try to make it better. So what you see here is a simulation of the same very high energy medium, how it would emit photons. And the photons are color coded. So early photons mean they're red, and then the longer they live, but maybe get more scattered, they turn green to blue. So the left is an ice cube, water and ice, and the right would be in the Cascadia Basin if you would put the same detector. So these lines are these detector lines, and each little dot, hopefully you can see that, but you can imagine each of these little dots on there is essentially one of these photosensors, which is light sensitive and can capture your images. So what you can see is the difference in ice, the photons live very long, they don't get absorbed, but they scatter a lot. Whereas in the ocean, they don't scatter. There's hardly any scattering. So if a photon is emitted, it goes essentially in a direct path to your photosensor. And you can imagine you can reconstruct such a track much more precisely if you have no deviation of the photons. Right? So this deviation, these crinkled lines essentially give you a large uncertainty. So this is how you get a huge precision into your reconstruction. Okay, so this is kind of what we're trying to do. So the top left would be a little rendering of the IceCube detector. The IceCube is also trying to push for a new detector, which is called Generation 2, which is really making a big, huge detector. So you can go one way if you want to improve the sensitivity, or you can make it precise and add new technology, and that's kind of what we are aiming for. So I'll leave the two images here because that takes a little bit too long. But these are essentially angular resolution plots where we can show that with the detector technology we have in mind, we can reconstruct these trajectories significantly more precise than what current detector technologies can. Okay, so what have we done if you have never heard of us? So we had some pathfinders from 2018 to 23 roughly, where we put sort of 100-meter and a few 100-meter long detector lines into the ocean, and we try to understand essentially the ocean down there, because you need to know if it's a good environment to build a detector. Currently, what we're doing, we have what we call the demonstrator phase, and I will literally can show you equipment here once I'm finished talking a bit, if you're interested. And we are currently putting together here a Triumph, this first line. So we will not deploy it in 25 anymore, and this will go in 26. But we are very close and have essentially everything more or less ready. And then beyond that, from this demonstrator phase, we hope that we can push for, if this is a great product, it's a great experiment, that we can push for a cubic kilometer detector, which can increase in sensitivity by a factor of 10 over the current ice cube detector. Okay, so I wanted to share a few things about these pathfinders told us. The first thing, here's basically, you can see two little lines of the pathfinder. So what the images from the deployment, what we did. So essentially, in simple terms, you throw them overboard. Then you have a remote operated vehicle which dives down to nearly 3 kilometers, and then it connects it at the ground and makes the connection to the power, to the backbone cable, and unfurls the line, and you will see if you can take the data you. So the first thing, which I also worked with Atlas, as I said, you always know when your LHC delivers beam. So you always know when you have to run your detector, but of course you don't know this if you do astronomical or astrophysical observations. The universe doesn't tell you beforehand what's going on. So one very important thing was to see if Ocean Networks Canada can actually be a reliable partner to that degree. So you can see here over the time period here of like 2 years, actually it was longer in the end, we achieved an uptime of nearly 98, 99%, which is excellent. So if, let's say, something great happens, like a supernova, or something explodes, something exciting in the universe, you don't miss something. It's very crucial because you can't be relying otherwise on knowing when anything happens. The other thing is the optical properties. So as you can imagine, the environment is very challenging. So we took 5 years of data, and the figure on the right essentially is that we tested the optical clarity, if you want to speak, so the absorption and the scattering, and to see if it is a good enough environment to build such a detector, because essentially you need very clear water, very still water, very consistent water. It can't change all the time. And this is exactly what you want. So it turns out that it's a very good quality water. The attenuation length, so how far photons can go before they start to get attenuated, is very high. So it is a good environment to build this detector. We also studied the backgrounds from potassium-40. These are radioactive decays, which are essentially also photon signals. And of course, one thing to understand, which is a challenge, which you can see on now I have my mouse on whatever reason, on the image here is kind of the growth in these detectors, which we call biopowering. So that's also something you need to understand, think of mitigation strategies in the future. Okay, so it's good for maybe 10 minutes or so. Let me tell you a little bit what we are building now. I will show you the line here because we have it. So we essentially build a 1 kilometer long ring. 1 kilometer is humongous. When you think of the highest skyscrapers, I don't know where you are, but even in Vancouver, we don't get anywhere near that size. And it's quite phenomenal to build things that stand in the water a kilometer tall. We will have 20 optical modules in there. And they're essentially this titanium ring, which has kind of no undersea connectors. So this was very important for us because these connections are very fragile in the ocean. And then we mount 2 instrumented hemispheres, which I will talk about more in a moment, onto this titanium ring. And the cable cable is also our backbone, which has timing, power transfer, data transfer, and everything. We have lots of calibration system, which I will talk a bit more about as well. And at the bottom of it, we will have this so-called string junction box. It's actually, and also over here, I can show to you how this looks in real, which is sort of our connection to the main mooring network. So I don't know, maybe you can see roughly behind me. So here's an image here of the optical modules. We're more or less all prepared. And on the right, you see one of my postdocs working with us and essentially doing a networking test with the main boards, which essentially is the main brains of these optical modules. And so we tested here 10 in connection to see how much throughput in terms of data, power, and timing. So okay, so I will let me give you a few moments maybe, because we did hear this a lot at SFU in my lab about sort of calibrations. This is probably the trickiest thing in an ocean environment, maybe compared to the ice, if you think of ice cube that I mentioned before, because you have ever-changing conditions. And so you have ocean currents, your detector actually will move. If you want to do very precise reconstruction of your particles, you will need to track at any time where your detector currently is located and is moving. At the same time, you want to understand your water really well. What are the optical properties? Does it change? We have yearly cycles, environment conditions. So we build a lot of calibration systems. One of them is light sensors, so laser sensors. So you can see them here at the bottom. We go back. That was too much. No, I lost the mouse again. So these are little lasers. These are very powerful lasers, so they can put out a lot of photons in a very, very short time. So they make a very narrow pulse. And what we can do, we essentially position them up and down the line. So you can imagine you shine up and you shine down, and if you have certain growth on them, on the optical module, you can make measurements with respect to the timing profile you see in this pulse. You go up and down, and you can understand essentially the absorption and the scattering length of your water column. We do that at many different wavelengths. This, of course, to be sensitive over the whole optical wavelength spectrum that we can observe these photons. We have a dedicated special calibration module, which you can almost imagine as a very bright light bulb. So we exchanged a few of these PMTs at the poles, and we put these kind of round, almost light bulb looking diffuser in there. So they're very high powerful laser boards underneath, and this is kind of a optical Teflon light bulb you can imagine. So the idea is if you step away maybe 2-3 meters from this whole sphere, and the two half spheres together, they emit a completely isotropic, very bright light flash. So when you have a detector array, as you've seen before, and you have them scattered around, you can imagine you have these very isotropic, very bright, but very short laser pulse or light flashes. So they allow you to do a lot of calibration from that as well. Also, this includes a camera, they study the ocean a little bit, study the growth on the module, and so lots of different things we can. Here you can see a few people actually putting this together. So this, of course, is not the laser board. It has an LED underneath to test the optical properties. But you can see kind of at the end cap here, this kind of shining light. I think if I do the next one, yeah. So this is now in the dark box where some student have tested that in this water tank. How this looks, kind of this with an LED light bulb, and you rotate it around what you would see from it. So you can imagine this now as a very bright flashing source. And then the last system I wanted to mention before coming to the end is probably it was one of the trickiest to develop because it is it is a different field than what we are normally used to, was this acoustic position calibration system we put together. So as I said, these detectors will sway in the ocean current, and you have to find out where at what time, at any time essentially, where these detector units are located. So you can do this a little bit like submarines, like with a sonar system. You can do acoustic triangulation. So we developed these small receivers, which is based on the piezoelectric technique. So essentially, you have a piezoelectric which is glued against the glass, and then you have some associated electronics to it. And we have on the seafloor autonomous emitters, and these emitters essentially emit fingerprints or IDs of different wave packages at known times, and then we can reconstruct just by triangulation kind of where your detector is at the moment in space. So we did several campaigns testing that also in the ocean. So you can see I can show you this in a moment as well in real time in live. But these little glued gray things are essentially the glued sensors towards the glass, and we were testing them here just in the Samish inlet, maybe in 150 to 200 meter depth. So the last test we did of the full system was kind of, as you can see on the left, we dangled our system from the boat just a few meters down into the water, and we had an interrogator. So interrogator is essentially the initial signal how to get the measurements started, which is also from the boat. And then we deployed these kind of 3 autonomous beacons somewhere in the ocean, as you can imagine. So this is only 150 meter deep here. And then we drove around with a boat, and we initiated a pulse to these blue pingers, and then they responded, and we recorded that with our module to test the position location. So as we knew the location of these pingers, we could reconstruct the location of our P1 module coming from the boat. And we could verify this with the interrogator because that was a very expensive, basically full-fledged system from a company. So what you see, you can kind of see on these plots here, these are kind of these spectrograms of acoustic beacons. So number A would be the release. B is what you see, the reflection. Of course, this reflects up and down, also on the surface. But then the really interesting ones, or the ones you actually want to see, is the C, D, and E in this case. So this is when it went to the pingers, they respond, and then C, D, and E are the responses from the pinger, which you can use for doing essentially the time of flight measurement. The other plots here just to push the principle of how you can find the peaks and how the signal roughly looks like. I'll skip through the details here, but essentially when we did that in the ocean, we could identify that we did nearly as well as this very full-fledged expensive system with our small piezoelectric elements. As you can imagine, they're maybe overall $100 then in the end per piece, compared to the system, which is $80,000 per beacon, essentially. So our small, very lightweight system basically got to the same position as this very large industrial system, which is of course great. I mean, it's only for this application. So by basically out of this time of flight measurement, we can go down to like 20 centimeters in precision, we believe, purely by what we got out of this test. All right, so I'm happy to show you this in a moment too as well. So this is in the end how this whole thing will look like. This whole cable will be, is just 2 meters away from you, looped on this deployment tray. The junction box is not yet, but it will lie underneath, and it will have a float on top. And this is how this will go into the ocean. Will be positioned, will be cabled, and then we can imagine an ROV is pulling a pin, and then the float will unfurl the line until it stands 1 kilometer tall. This is how it looks just in front of me. If you're keen, I can show you around a bit and how it looks in real life. Here's a little video. Oh, how this was flying essentially through Triumph. If you've ever seen the Maison Hall, you can see the big thing. So it's a quite large, extensive deployment frame where the cable is wrapped around, and this kind of aluminum wrapped building at the end, or not building, but this is exactly where I'm sitting right now and talking to you. So this is the clean room where we eventually put this in. Let me see. Let me see if I have much more. No, I don't. Okay, so the last thing why, which is kind of a non-physicsy interesting topic sometimes, is like why is this interesting also for climate and ocean science? And it's not immediately obvious if you don't think about it. But and there's a lot actually, but it's just one list here, and it's in some words it's purely the scale. And so you have 1 kilometer long instrumented mooring lines which are attached to the ocean floor. If you compare this to normal installations, which are usually on the order of meters or tens of meters, and they have an operation cycle of several months until they get removed, and then the data get read out. So the difference here is really the scale of this experiment and the duty cycle. So if you in the future then take all the mooring lines together, you get a really gigantic instrumented length. And what we do, which is kind of to some degree our, let's say, nuisance for physics, is exactly what is interesting for this, to monitor the environment. So this is we constantly monitor the water properties, the bioluminescence, the salinity, temperature, the currents, and also their changes. So all of these are very key markers to study the ocean. And kind of for us, it is a key to understand our detector performance to do physics. In addition, we have a huge acoustic sensor array to track the positions of our detectors. And of course, you can use this also as a listening array. And as I said already at the start of this kind of slide, so it's literally the scale, the precision, and the duty cycle which makes this exciting for also non-physics applications. Okay, so that's just a picture of us when we were in Vancouver at the last collaboration meeting. So I would say 2/3 of the people currently working on this experiment. And I will pause here, and if people are interested, I can A, answer questions, and then B, also show you a bit around maybe what's around here.
Yeah, thank you. Virtual round of applause. Sometimes people take a second to put things in the chat. Do you want to go ahead and like show us around a little bit and then give people a second to type?
Sure, I can. So behind me, you see now all of the optical modules. We kind of they were here. So they were in principle made and kind of put together the PMTs inside the glass spheres in Munich, Germany. Then they came here, and at Triumph, we kind of put everything together. So the remaining electronics, we put all the calibration devices. I can kind of show you, for example, here you can see now an acoustic one. This is include an acoustic sensor. We have where are the directional flashes? See here quite well. So here you can see all these directional flashes. So we basically integrated them. We did quality control of them here, and this is kind of where this all happened together. I can show you the line in real life. So the line came from Denmark, so it's huge. You can see some postdocs actually working here as well.
Yep,
And
there's different voices.
exactly. And then what we are currently putting together, so here you see one which is mounted in one of these positions. So we have these kind of stacks where the optical modules will be mounted. And hopefully when the ROV or when the float pulls it up, this will nicely slide out when everything unfurls. And here we're currently making, this is not fully connected, it's just essentially the I would say the physical overall connection inside the optical fibers are not yet connected and the power is not yet connected. But the scale is quite impressive. I mean, you can see my hand here, but this is massive in terms of the cable. Yeah, it's a decent size, but it has to survive a very hostile environment. It's a little bit like space, expensive and very, very hostile to do science in.
Yeah, cool. Thank you for the tour. It's at least personally, it's very fun to see all the little they sort of look like bug eyes with the PMTs and
Yeah.
and you were showing me around a little bit before, but it's cool to now that you've gone through the talk to see what all the little calibration bits are for. All right, I mean, no comments in the chat, but I did have a couple. So I guess one, since this is aimed at people, undergrads trying to figure out what to do next with life, suppose I am interested and want to get involved. What's like the next thing that you're working on that, like, if someone was to get involved right now, what would they be doing?
So it actually, I mean, we're still in that phase. It's very unique in a particle physics experiment that you could be involved to put this, to actually develop it and put it together. So in IceCube, for example, I was able to build detector components, put it sort of together and deploy them, but I could not be part of the development because the cycle of such experiments is so huge these days. If you think of Atlas at the LHC, you know, like this is a 30, 35-year-old experiment. So you have in the moment still the chance. So this is our first line. We know already several things we will change, several things we will improve. So you have the chance to actively still contribute to the development of the detector, to figuring out how this goes. You know? It's very rare. You probably don't believe it, but the cycle is so massive that very few students get the chance to do that. Of course, you also get hands-on experiment that you can actually put this thing together. Yeah? And of course, now the whole forecasting, the simulation, the data analysis part starts as well. Yeah? So once we have the first line in the water, we will, this one, we can't do too much neutrino physics yet. We might be able to see a first neutrino here and there, but it has to kind of almost go down the line directly. Huh? So that does happen, or go up. So it will be very hard, but then as we have more and more lines, we will verify that the detector works as we do. We do lots of data analysis, background, lots of calibration. We will start to do pointing analysis, which is, it's called moon shadow. Like, you know, it's another concept which probably is very hard to understand, but for these kind of telescopes, you have no positive source. You can't just, let's say, dark matter experiment, they put a radioactive source in the detector to calibrate the detector. Or the LHC goes to a test beam and fires particle beam to detector elements. We don't have that. Right? So how do you verify the pointing? So we have one source, which is the moon and the sun, but it's a negative source in cosmic rays. So because it shields essentially a little bit the cosmic rays. So instead of having a positive source that emits, you can reconstruct a little dip. And when you can reconstruct the dip, you can verify that the dip is actually there where you're supposed to find the dip. And that means you have the capability to point back in the sky, you know, like when you have a active galactic nuclear or a supernova which is exploding, you actually find it, and you randomly point to a different place in the world. So these are all the things you would start to work. So it's literally the whole full spectrum, and it will grow and grow and grow until, of course, hopefully the detector grows to the size where we would do the absolute cutting edge neutrino physics results.
Many things. Um, thanks. We do have one in the chat asking about how the detector will be assembled and installed in the ocean. Yeah, take it away.
So assembled and also fully tested is kind of on land. Then once everything is together, without the float, we haven't figured that out yet if we have use a big tank or if we actually dump it into the ocean, like somewhere from a harbor, because you want to test for so-called ground faults there. So the worst thing in the ocean is because the ocean is salt, so actually it's quite nasty if you try to drive electrical current through cables and you have somewhere a ground fault. So it would be basically catastrophic for the detector. So you make a test on sort of shallow water first, and then a boat will drive out. The whole assembly will go over the basically overboard, will be lowered down, and it's kind of with the buoyancy, how everything is calculated, it's not that heavy. So an ROV can actually pick it up. It can carry a few 100 kilograms of water, the ROV. Can pick it up, place it exactly where it's supposed to go. Then the so-called underwater mateable cables, they're massive, also exceptionally expensive, where you can essentially imagine this ROV just makes a connection of these cables and makes the connection, and then you unfurl it and it goes up.
Cool. Thanks. Bit of a process, and we got a second one here about how you differentiate between like neutrinos versus other sources of light in the ocean.
Yes. So so the so one thing that is very difficult. So as I said before, so you have muons which come from the atmosphere as well. We all know of the kind of cosmic or atmospheric muons, and they will also reach the detector, but they can only come from kind of above and towards the horizon. So if you have a detector that essentially reconstructs a muon track which comes from below or kind of just below the horizon, then you can do this very accurately, and you can be very certain that this is from a neutrino-induced muon. You can have some issues there, but especially in water, this works really, really well because these detectors are so precise. IceCube has a bit more of a, let's call it fake rate there, because it's a bit harder with the scattering in ice, but they figured that out really well as well. You can also do, if you have a very large detector, this is what IceCube does, but you need a large size. So for P1, this would be in the bit later stages. You can use outer parts of the detector, so the outer layers, as a kind of an active leaker. So muons, if they come in and they exist already outside, then they leave light throughout the whole detector. But if you have a downgoing neutrino that interacts inside your detector, then the neutrino will leave no light. Then it will start with a basically emitting light when it is interacted and created a muon again. So you essentially would look for a quiet detector where suddenly the light starts, which is still downgoing. So this is also how you can identify, usually at higher energies, neutrinos which are created inside the detector.
Cool. Thank you. I'm also realizing we are slightly over time, so maybe we could take one.
Yeah.
How are you doing for time? I don't mean to push it.
So there's a question about
Yeah, there's a couple
internships.
more.
Yeah.
There's one about what happens if the detector optics get ruined under the ocean, and I assume it matters what type of ruining. Like if a whole line gets severed, that's a larger problem than just if one PMT goes out or something. Um,
So
and
it's
then
a
there
good
was another
question.
one of
Yeah.
internships.
So with the detector optics, I mean, in principle, we design it like if you have one failure, that the line is not a complete failure. Like it's not that it's catastrophic. But of course, that module is gone. So if let's say you have an implosion in that module, that is gone. It depends a bit how catastrophic that is. We of course pressure test for this. So we did several of these tests that we have a lot of safety margins that this really should not happen. But I mean, who knows? In terms of individual PMTs, if the PMTs go out, then you just have less light sensitive components essentially until eventually, let's say, more and more PMTs would die or age or so, and it's just less good. If you have increased biofouling, your efficiency just gets reduced slowly by a few percentage. So there, I haven't mentioned that we have lots of different mitigation strategies for that as well, but I think it's a bit much for me to discuss that.
Thank you. And in terms of the question on internships and such, maybe do we just give an email? Is there a website? If people are trying to get in touch, what's the best way?
So there will be always so we currently have at University of Alberta, SAC, and also in Queens in Canada. And so I definitely know University of Alberta and SFU. We have per year several USRAs, so these summer student positions for P1 and associated activities. So they're announced as well on the webpage, so you can look for it. You can. There's of course a competition to get them, but yes, they're there. Actually, quite a few opportunities, I would say.
All right. Thank you so much for your time. I think this is our first lab tour in this set of
Yeah,
lectures,
no, it
so
was maybe fun.
much appreciated. And
Okay.
I guess that brings us to the conclusion. I'll stop the. Oh, I forgot to stop the recording earlier, but we will stop that now.